Good afternoon. Well, I have the pleasure and the honor to introduce the speaker of this afternoon. Olivier Baverel has been all the afternoon with us, not just now. He has been assessing one of the final tasks of our subjects in the Master of Parametric Design-Architecture. So he has seen what we have done, and now we like a lot to see what he has done, which is much more interesting than what we have done, probably. Well, Olivier is teaching in both schools in architecture in Grenoble and École de Ponts Paris. And this experience of teaching architects and engineers is something that is very interesting in our field of research, in our field of teaching, in our master, and I suppose in this afternoon talk. He has been also working in research in 2 labs in France, and he is editing magazine of research. So all the aspects of research and teaching are covered by his experience. So I think it will be a very interesting talk this afternoon, and I think you prefer to hear him than to me. So when you like.
Thank you, Ramon. Yeah, so I changed just a little bit the title of the conference. It's Make Complex Structure Affordable. Just 2 or 3 words on where I work. I work for the School of Architecture of Grenoble, and also the School of Engineering called École des Ponts et Chaussées, where within this school there's a lab called Navier, and this school is in a suburb of Paris. I'm not sure if it's okay to stay this way. It's maybe because I'm close to this one. Okay. So within the Navier lab, there's a team which is called Architecture, Material and Structure, where we work mainly on what we try to call a construction-aware structural design. I'm going to detail, and my presentation will be mainly about this. So within the École des Ponts, the strength is that we have a lab specialist in structural mechanics, and also in material science, and also in life cycle analysis. We have another lab which is called Gaspard Monge, who is an expert in computer science, in vision and artificial intelligence. And we have a company called Al Robotics that is working with us on sensor and controls. So let's go first, why we do a complex, why we build complex structure. Because obviously making a cube is not the optimum. If we want the structure with the least thermal bridge is the best is to do an hemisphere. If you want to get a more solar gain, you should make a 45 angle with the south. If you want to pack some volumes, then you better do some cubes or parallelepiped rectangles. And if you want to do structure, then life is much simpler if you do tetrahedrons. And of course, having only the optimum of each solution doesn't give you the global optimum. And you have to find a way to find a global optimum. And a global optimum for what? Well, it's certainly for sustainability. You all know that our consumption of any material is getting into an exponential, and we have to reduce this consumption within a very short time if we want not the planet to survive, but humanity to survive. The planet doesn't care about us. Okay, it was there before us, and it will be there after us. It's just a question of humankind. So we strongly believe that construction-aware structural design will help, and it's not a complete answer to the problem, but will help to maybe use better the resource. So having said that, if we look at a latest publication from Catherine Devol from École Polytechnique of Lausanne in Switzerland, she looked at stadia, and she looked at the amount of material used to build the stadia. And you may know the beautiful stadia from the Olympic game of 2008 in Beijing. And so in terms of complex structure, we're not yet there in terms of consumption of materials. Well, if you look at the stadia of 2012 in London, it was far much better. So there's been people understood that taking and using modern tools need to get some optimization, not to consume too much materials. Remember, or maybe you are too young, but in 2008, the price of the steel in the entire world increased. And all the big companies of Europe lost some money because the price of steel went up due to the building of this stadium. Okay, I could show you also on the CO2 emission, and it's the same graph. So our proposal is to investigate better the mechanics of materials and use the materials efficiently. It's also to revisit the roots of geometry. And at the moment, we're using tools that are not adapted to what we want to do. And we, of course, want to use cleverly digital tools and artificial intelligence. And this will be the last part. We're building and we're doing many things at the moment. And we're destroying them at the end, getting into raw materials at best, or they get to a dump. Can't we reuse directly elements to make and save and have a better life cycle analysis? So first, think mechanics of materials. If we look at the first iron bridge that you probably all know, it looks mainly not as a bridge, a steel bridge, but mostly as a bridge of masonry. So a new material came out, and they copy the solution of the previous materials. And we had to wait 50 years and even more until Navier developed the beam theory that you all know, the equation, I suppose. And 50 years after, you had Gustave Eiffel, who built some bridges that take optimally the use of the materials, where you have trusses or even trusses within trusses to get a really lighter structure. So, but it took some time to do it, and it was not straightforward. If we look nowadays, new materials that came into our industry, it's the composite materials. So mainly glass fiber, and you know it's quite cheap, or carbon fiber, a bit of carbon fiber. But if you look at all these details, I zoom on to these details, and it's mainly copying steel. But you all know that steel has some fantastic properties, which are elastoplastic, and it's not a brittle material. And composite material is a brittle material, fragile, and not ductile. So you cannot copy straight what is built in steel directly in composite material, or you will never win. Steel will always be better. So, but there are some strengths into composite materials. It's lightness, the capacity of prefabrication. You can put some, integrate some functions, for instance, optic fibers to know what is stress within the structure at any time. And you don't have any problem of corrosion. But you have to remember that these materials have a low Young modulus. You have to remember that most of the slender structure made out of steel stand due to the Young modulus, or the rigidity of the material. So here we have a material which is more or less 10 times softer than steel. So you cannot directly compete against steel. Of course, there are other problems. It's difficult to actually assemble, and there's no ductility, as I mentioned before. So you either copy what is done by steel, and then you will never do better than steel, because steel, the solution provided by steel is optimized for steel. So with composite materials, if you copy steel, you will not do better than steel. You need to find a proper way to use composite materials. So here, an interesting example, you can always try to do pole vault with a steel steel pole, but it's not going to work. So you have to take the advantage of flexibility, certainly for stiffness. So one famous solution is to do an elastic grid shell. As you all know, you start from a flat grid here, which is, you could look at it as a membrane without shear rigidity. So it means you can access to a vast variety of forms. You get your 3D shape. Of course, nowadays, tools are available, easily usable to make these forms. And after, you brace the structure. Here you have a structure made of several arches that are working together. And here you have a shell. And the shell, by adding only 50% of material, you will have a shell which is at between 15 and 20 times stiffer. So you change your structure, and you change completely the stiffness of your structure. So here are some pictures of structure what we built in 2005 and 6. Here it's a crane, but at the beginning we used to lift it by hand, and it was difficult. So we had in the last 15 years, we had many tries doing some useless things. So we did many tests here to know actually what is the best, the maximum stress we can allow to these elements. Remember that for those of you who have designed steel structure, you know the yield stress of steel. You put a little coefficient of safety, and then you can design a beam. Here, the coefficient of safety is 3. It means you use only around 30–35% of the capacity of the material because of many safety coefficients that are needed. So it means when you look at only the fiber, glass fiber can be 2,000, could be 10 times better than steel in terms of strength. Well, when you make the materials, then it's only twice better than steel. And when you look at the stresses with the coefficient of safety, then it's lower than steel, okay? In terms of strength, not in terms of Young modulus. Okay, so if I resume a bit what we did many prototypes. This one is the most famous one we did 10 years ago. We did a real prototype for Solidays Festival in 2011. And we did a temporary cathedral of Créteil in 2013. We also did many other little tests. For here, an hybrid structural skin. So you know that Making a grid, getting a 3D shape is not difficult. But it takes you a lot of time to do the bracing because you have to get into the structure and also to put a cladding on top of it. So here, there's a grid shell, and on top of it, there's a 1.5 centimeter high-strength concrete with our specific formulation from the École des Ponts. Okay, so here's a view of internal view of the Solidays Festival structure. It's always interesting to see the path of the elements, which is not following geodesic or whatever. And it's also important to know that we span more than 14 meters with a cross-section of 4.2 centimeters in glass fiber. So I think it's good to tell you or remind you how we design this, or the design procedure of this structure. You see it goes in 4 steps. The first step is to get a 3D shape, and after to mesh it, relax the mesh, and after to do a classical structural analysis calculation. So we as many projects have seen, we started to do mesh on a flat surface, and we used to push it, and then you get an uncontrolled 3D shape. And an architect asked us to do a certain geometry, and we told him, well, wait, because we have to find a way to find your shape from the flat surface. So you have to do a sort of reverse engineering. And this was not just impossible, it was almost impossible. So the way to work, the best way to work, is to find a 3D shape given by an architect or a designer, and you have to mesh it. And this is the main point. So if you want to, well, you do a 3-dimensional structure, if you want, or whatever. But how can you check that this geometry is buildable? If you have to run all the process, then it's going to be too long. So there's a simple check. It's to look on the global curvature of your structure. And if you look on the global curvature, if you know the cross-section of the element you expect to use, you know the radius of curvature, or the minimum radius of curvature you can allow. Okay? So just by looking at the Gaussian curvature of your structure, you know whether you will be able to build it or not, or break the element while you put it in shape. So that's a first step. Without many calculation, you know whether you can build the proposed geometry. Okay, so that's important. Well, once this was the first shape. We corrected the shape in order to have a curvature that was not too small. Of course, it's taking the simple Navier equation. So that was that helps to work directly with the designer in the shape you want to use. You can work real time. And after, once the shape seems to be okay, then you have to mesh it. So we made our own tool using the compass method developed by Fraiotto. And you choose 2 lines, and after you have to extend the surface you did in order to be able to mesh it. Once you mesh it, you cut at the plane you expect to build it. And after you have your structure. You see that there are no automatic strategy to mesh your structure. You can choose these 2 first lines, and it will give you a surface that can be meshed or not meshed. Here you see we had a high concentration of bars here as well, and it's completely useless. And it's not interesting at all to get it, so that's why we didn't take this solution. And we took this solution, which is far better. There's no automatic tools yet to find the correct mesh. And there's an important question is, can I mesh any surface? So as you may know, the École des Ponts has many mathematicians working with us. So we did a PhD on this topic. Can I mesh any surface? You have to know that it's called a Chebyshev net. Chebyshev was a mathematician working for the Russian army. And he was working on the clothes, how to cut the clothes. Because at the end, your clothes is a grid shell. Huh? And you can see that you cannot do any surface with a grid shell because you have to sew sometimes. Okay, so can we mesh any surface with a Chebyshev net? The answer is no. So, final step of the design. This is the structure we wanted, and we have to not unfold it, but spread it flat to actually make it. So here's the flat configuration of the 3D shape. You couldn't find it from the, well, you couldn't do the opposite way, huh? Otherwise you're a genius. Huh? And after you do, you have to relax here, sorry, it's only geometry. So you have to relax the energy, the bending energy you have within the structure. So I don't show the step, but usually the structure does not move too much. Once you have relaxed the bending energy, then you can do a structural analysis, taking into account the rest of the bending energy you already have due to the bending. Okay? So after you have to build it. So you build the structure flat. You land 2 big cranes, 30-ton cranes. You see on site, there's already all the foundation are there. All the places where we have to put the elements is known. So you leave the structure with the 2 cranes. We did some calculation before. Of course, to get more or less the shape. And after, if you used to be a rugby player, then it's quite easy. You have to push to explain this part has to go to this foundation. And as you get some bending energy, sometimes you have to push a lot. But it more or less works. And of course, at the end, you have this. Once again, this one is structure built for the Cathedral of Créteil. You have a span of more than 15 meters, and once again with a cross-section of 4.2 centimeters. It was more or less the limit of what you can expect with this cross-section. It's a hollow cross-section, huh? It's only 2 millimeters thick. The couplers are swivel couplers, well known in the scaffolding industry. So we developed all the tools quite a long time ago to find all this shape and calculation. It was a PhD of Cyril Dout, and he was graduated in 2007. As typical French, we had all the tools and we didn't release anything. And Daniel Piker retook the work that we already took from Chris Williams, and he made the fantastic tool called Kangaroo. So we tried to go further, and of course, the model we used to make is only with bending according to only one axis. And here, by taking rectangular cross-section, then you have to take the 2 axes of inertia and also torsion. So taking torsion is quite a complex task. This was our latest PhDs. So once again, we have a tool. We haven't released it yet, hopefully soon. And it allows you to perfectly take torsion. Our colleagues from IBOA EPFL already worked on this topic. Some students have shown some work. And it was a collaborative work with us and Sinan Abai, who did his PhD at that time. So constructibility is also mathematics. So you have to know that if you want to do put a Chebyshev net on a surface, there are some limitations. And the integral of Gaussian curvature, I don't know if you see what I mean. The maximum Gaussian integral of curvature that you can get is pi. I shall remind you that for a sphere, the integral of curvature is 4 pi. Okay, so let's say you cannot cover more than any shape with more than pi integral of curvature, except for the sphere, where you can go to more than the hemisphere, but you cannot do the sphere anyway. So that was a big question, and we found many papers saying, no, it's not possible. So we said, well, the PhD is finished. We cannot do it. So we said, well, if we cannot do this, we might be able to cover more by doing some patches or by doing some singularities. Doing some singularities, it means here, the valency of the node, the number of elements that comes to the node, is not 4. Okay? So here you see a valency which is 6. Here you see a valency which is a lot, more than 40. And here, so you can find the singularities. Well, I might not go too much into the maths, but normally the number of singularities that you have to put is equivalent to the Gauss-Bonnet theorem, according to the genius of the surface you use. So for instance, if we call it a rosace, to cover an ellipsoid, you know that the genius of this surface is 2. Then a rosace is a singularity of 1. You need 2 singularities to actually cover a sphere or an ellipsoid. It's like in a bag of potatoes, you see. You have, the mesh is a Chebyshev net, but you have 2 singularities. If you look at the potatoes net. Anyway, so that's yeah, some students have shown some problem today. So here we can see clearly that we could do, within the same principle of having a sort of tube. Here the tube would be elliptic, with a certain organization of the elements. Then you could do, with one singularity, get the 3-dimensional shape. It's quite promising. We obviously try it, but if you consider here that it's a pin connection between the patches, when you release the bending energy, then you have more something which is not smooth. It's more something like a polyhedral form. So we did some work. We're going to soon release a paper. So we took the Solidays Festival structure and tried to match it with some patches in order to get lower bending energy into the elements. So this is the patch and the mesh that we built. So I carry on. You all know that the biggest values that we can get out of a project is certainly on the concept and design part, and it's all in the parametric design phase. And I would call it traditional beam. what is good for production and operation. But if your project is not good, then even if you're the best BIM manager of the world, your project will remain not good. Okay. So this is the important part of the project. I don't have to convince you. But we have a problem. You see here, it's a Citroën DS that was designed in 1957, and where all the algorithm that you're using, most of the algorithm you're using at the moment in the NURBS tools are coming from. So this was designed by, not designed, but the algorithm was proposed by De Castelgio, I don't know. And as he was working for Citroën, who was a private company, he couldn't publish his work. And it's Bézier, who was working for Renault, who was a public company at that time. He could publish. And you know, all know the Bézier curve, but at the end, it's more the Castelgio curve that we could use. But there's something you see a bit strange, is that we're using algorithm developed by the automotive industry. The automotive industry doesn't have the same requirement as we have. If you want to do this part of the structure, it's quite simple. You design it, you make a press, you put 30 tons on top of it, you have your sheet of metal, and then you have the form. For a large building, we don't have such a press, and it's rebuilding with parts of elements. So our strategy of construction is completely different to building a car. And if you look at the history of architecture, it used to be a concatenation of known surfaces, known how to build them, how to mesh them. And in 2004-5, people said, oh, well, forget it. I'm going to use NURBS. But NURBS, the problem is that in our industry, we need a mesh. You need a form, but after you need a mesh. In our industry, you don't need the mesh. Huh? And if you need a mesh, then you need some certain properties for your mesh. And on the NURBS, you can put a mesh. This mesh doesn't have any good properties. It's simply not buildable. So you have to find, you make your form, you put a mesh on it, and after you have to buy the knowledge of a geometry to optimize your mesh, to allow you to carry on thinking about your project. So this is a really weak point, I think, in a modern architecture. If you need 25% to help you to just make a form, then the work of the architect will be lost. Or people won't get the point. So you see, we have to think differently. Just back to the roots of architecture or architectural geometry. This is a very nice drawing from Gaspard Monge, who was showing the main line of curvature of an ellipsoid, where you see here you have two singularities, but in the entire ellipsoid you have 4. And at that time, with no knowledge of differential geometry, he was able to show the main lines of curvature. This was, all this development was needed for stereotomy. I don't know the word in English, but I think it's the same. And it's the art of cutting of stones. And this was, at that time, was developed all the drawing and geometry. Mainly by Gaspard Monge was one of the leaders on this topic. So if we look nowadays, constructions, they are very nice architecturally. But here you see we have a valency of 6 within the grid. But if you make a mesh with a valency of 6 and you start to give a thickness, then there's no point, no, it's not possible to get a structure without nodes without torsions. You will always end up with nodes this way, unless you make a sphere. If you make a sphere, there's a very easy way to do it. You do just a scaling, and then you have nodes that doesn't get any problem. But as soon as you have a change of curvature, then you cannot scale it. It won't work. So remember this, having a structure, having a form, having a mesh is very difficult, and you really need certain properties to actually make it buildable. So this is all the work of Potman, who did a very interesting work on optimization. You give him a mesh, he will optimize it in order to have quadrangular panels, nodes without torsion, and all these things. But the big question is, can we have surfaces that are directly buildable without optimization? You see, for you to be able to make things in real time without the help of a geometer, otherwise it's not possible to design. So the answer is yes. Just as an example, you can reinterpret the work of the old masters just by taking two lines here, the blue one and the green one, the orange one. By simple geometry, you know the coordinates of 3 points. They can describe a plane, so it's quite easy to find the coordinate of the 4th point. And all these elements are planar. So we called it, it was a PhD of Romain Ménil, and we called it the marionette mesh. So it's very light, very simple for a designer. You choose 2 lines and you get straightforward quadrangular mesh. You can, as you have almost a real-time tool, you can do easily optimization. And also, you can not only do fast calculation, but by this way, you can have a space of research, of search, which is much higher than only the NURBS. Remember, the NURBS is a polynomial equation that you use, and you cannot do any surface. Okay, you cannot do any surface. Here, the space of research is higher than the NURBS. So the optimum you will find structurally has a chance to be better just because your space of research is higher. Also, when you start to use NURBS, it's very difficult to do a SEES. Okay, like here. It's not so simple. With the algorithm I just shown, it's just straightforward. But here I was speaking about geometry, but I think we have to go beyond this. It's to think in terms of topology. Okay, and depending on the structure you want to build, and with some certain particularities you would have. For instance, you want a point here, an opening here. What should be the mesh you should have? And so we're developing a PhD at the moment with Philippe Bloch and ETH Zurich on this topic. And it's sort of towards topological finding to help the designer also according to what he wants in terms of shell and what are the particulars he wants. He will have a mesh according to the topology he's looking for. So that's, I think, very promising. We're developing a tool at the moment. Another PhD is with the company Viri and the consultant test. Here, it's how to build with developable strips. But yeah, there are many tools already available. But the idea here is to really well understand the discrete differential geometry problem in order to be able to see directly from the strip you're building on the floor the three-dimensional shape you're going to get. So here's an example of what we're able to do. And the last one, which is quite interesting, you see in terms of interesting surfaces, they are the constant mean curvature surfaces. Okay, mean surface, it means it's the sum of the two radius of the surface you're studying. And if it's constant, there's also, of course, the minimal surfaces, but there's also all the inflatable surfaces. So if you look at this type of structure, they are fantastic in terms of buildability. You have node without torsion. You have planar elements. You have the thickness. You see, it means you are edge offset. You know all these terms. Edge offset. The edge offset is the same. In one direction, they're all the same. It means these elements are the same height, and all of these are in the same height as well. So you have many interesting properties as a builder to use this type of surface. And also what is interesting is that you can use it in many different boundary conditions. So we call it perfect nodes, the one who don't have torsion and are edge offset. So that was about mathematics. Now I'll go a bit faster. Okay. I'll speak quickly on computer science and robotics. And, there's a big question on how digital and robots may help. So we have some facilities in the École des Ponts, 2 robots that are one on a track and a static 6-axis robots. I will show you. We have another robots to do 3D printing. And we're trying to run some 3D printing differently from what we see usually. We're working with a startup company called Este. And the idea here is to use 2 robots, one with foams and another one that's going to print in order to make directly a space frame, in order not to use too much material. You all know that 3D concrete printing costs a lot of money. It's very often high-strength concrete. So if you want to have a life cycle analysis which is acceptable, then you have to use it, not to use so much. And you all know that the problem of 3D printing at the moment is to have some reinforcement. You're not compatible with Eurocode 2 at the moment, so it means you cannot do much. So you have to reinforce them. So we need a smarter and adaptive robots on site. So this answer, I don't have any answer yet. There's plenty of work to do. We have to take the best of both worlds, of robotics and of the humans. I don't think you will have only robots on the sites, or it may not be the most efficient solution. So we had a PhD, I go quickly on this, saying, do a robot can recognize some elements and directly pick them to build a structure? So we used artificial intelligence or neural networks. And what is, well, I was not an expert. Well, I'm still not yet an expert. But what is amazing is that you learn to the robot. You show him, here's the robot, here's the cube he has to pick. You create numerical pictures, something like 500,000 numerical pictures. And he's learning from these pictures. And after learning it, he's able to pick up actually the structure. So I have a film, but it's too slow. I won't show you. But he is able to pick 5 blocks. You have some blocks. You put them on the floor. There are 3 cameras. And he takes some pictures. And as he's seen 500,000 pictures before, he knows how to recognize where is the blocks. And what is amazing is he learned not in a real way. He learned numerically with artificial pictures. Because if you have to do 500,000 tests, then it will take you all your professional life. So it's not efficient. But with this way, it can learn very quickly. So materials, mathematics, and robots. We made lastly a new pavilion. reusing some known strategies with some partners. ABB, you know, it's a robot maker. Wirtz is a screw makers and more than this, of course. Schunk is a supplier of any system that you can add to your robots. And Simonin is an expert in wood manufacturing in the Jura region, next to the Swiss border. So here's a final view of the project. So it's some people call it reciprocal structure. We call it Nexorade. And what is quite new in the system is we develop a new algorithm that takes from a reference surface, you make a PQ mesh, so planar quadrangular mesh, and after you transform it into an Nexorade, just by translation, because translation is just a linear system of equation compared to rotation, where it's a non-linear. And after you get not only a Nexorade or a reciprocal structure, you get a shell Nexorade, because these elements are still plane. So that's an important point. So your structure can behave as a shell. Well, after you get all the screw positions, the beam geometry, fabrication data, and you go for it. So here's the site. We have a robot on a track, which is picking a beam. It's going to cut it into the correct dimension. It's going to make the hole for the screw. And it's going to be milled by this robot. So it's a 13 degrees of freedom system that work together. It has been a nightmare to explain the two robots, but they were in the same world, okay? But they finally accepted. So here you see one robot is holding the beam, and the other one is milling. So the screwing process is extremely simple. It's the advantage of this blown up node. So here's the team, and the team of students that have. One last element is a question of reusing element or construction elements. I will show you only one example, is this one, and how to reuse bicycle rims to make a truss. So it really works well. We were stupid because we used OSB here, and it fell into tension. You have more than 1 ton of bricks on top of it. But there's an interesting question. You see, we produce 4 billion soda cans per day. 4 billion. It's a piece of engineering. You see, the wall is only 80 microns thick, and we, at the best, we transform it into raw materials, or maybe it's gonna go to the oven. But can't we reuse the technology that was embedded into this structure? So that's an interesting question. And as we don't have, we live in a finite world and finite resources, sometimes we may have to think about a second life of a structure. Or all the objects that have a short life, we should design them for a longer life and a second use. So this is a provocation, of course. But what is interesting is that we reuse 80 or 90% of the capacity of the wheel, except the crank size, which is completely useless for our use. For the rest, it's pretty good. And do not forget about always the question of assembly. Here, the valency, maximum valency of my structure is on never more than 3. Because you cannot see very well, but there's a bracing element at each side of the structure. So it's always a valency of 2 or 3. So it remains Okay, so see here the team. I'm not alone. I have my boss, who is an expert in composite materials. Especially, he made many models and fine models of composite materials. So that's why we've been able to do Gridshells. And here's Nicolas Roussel, who is an expert in concrete making, and Laurent Stephane, who is a mathematician that helps us a lot on all the mathematical problems we have. And Cyril Dout, who's a colleague. Romain Ménil, who's a former PhD student, and all the other are PhD students. So you can, if you're interested, you can follow us in ThinkShare. And also, for those of you who don't have access to all the networks of papers, there are many papers in ResearchGate. So please go and have a look. So it's finished. Thank you.
Well, that's a term for questions.
Hi, thanks for the talk first, and I was wanting to go back to your talk to the multi-nets part and the Chebyshev nets, and I was investigating a little bit about it, and I wanted to ask you, how do you design the multi-net patches? So what are the overall restrictions, or what is the trick, basically? So because doing a Chebyshev net is easy, but finding the points where multiple nets will collide might not be so easy.
Of course, it's not easy. It depends on what is your design criterion. But there are still some tools to be designed to actually help a designer to use it. There's no obvious strategy. We're gonna release soon a paper about it, and it's not that easy to.
Yeah, be sure to read it.
I'd like to make a question. You talked about meshes and cladding. Have you any one of this group working on claddings? Or cladding is just something left for the others?
As you can see, we're not expert in claddings. We, on the construction-aware structural design, we're more in a mathematical part, and we're less on the practical part. So, of course, for the last pavilion we did with shell next arrays, the cladding is...
for the cathedral, too, there's closed.
It's directly the wooden element.
Yeah, but it's something that you use. And you have to think.
Yeah, of course. It's what I often say. Even you have a good form, you have a good mesh, but you have done only half of the job. Now you have to transform it into a constructive system. So in some images, I've shown only half of the job.
Okay, thanks.
How much of your industrial partners use your tools after your research?
It depends, I would say. Sometimes you're too much ahead, and they simply don't understand what you're doing. And sometimes they're really interested and they use it, and it makes working together for decades. It depends on the size of the company, and if it's a huge company, it's difficult because people who are ahead on the top of the company, they have a lot of stress of many other sides, and not especially on research. So sometimes the work or the collaboration is easily lost. When it's a medium-sized company, the people stay, and then you can really build knowledge together.
you've said that you are using swivel couplers for connecting the two pair of rods. Have you found out something better?
Yes. Yeah. We're developing new solutions. We try to. Thanks to 3D printing, we can make many models now. We are working with a company called Aremon, who invented the buttons of the pressure buttons, and they make 500 patents per each decade. And they helped us a lot. Soon you're gonna have new solutions.
Well, if there are no more questions, thank you very much again for this nice talk.
Thank you very much.